All right, this is Honors Algebra 2 and Pre-Calculus. We're doing section 4.8 in Pre-Calc. This is the third video in this section, the last video in the chapter. So I'm not going to give you a test on this material, but it is worth a quick video just to introduce you to the concept. You'll likely have one or two homework questions on this particular topic in this course, but you won't see it on a test, and it will likely come up in your physics class in more detail if my memories from my own 1996-1997 physics class are correct. So recall that trig functions are periodic. They repeat over a time interval called the period. So there are tons of systems in the real world that behave this way, right? Systems that oscillate like a pendulum or a spring, or vibrate or rotate, right, like a wheel or a pulley, or move in waves like sound or water. They can all be modeled extremely well by trig functions. So these types of motions are generally called harmonic. So this is an image from your text, and it shows a ball attached to a spring, right? So let's assume ideal conditions. There's no friction, there's no air resistance, there's nothing wrong with the spring, everything's ideal, everything's perfectly elastic. If everything were ideal, this ball on the spring is going to move in a harmonic motion, right? So this is equilibrium, right? It can move down 10 centimeters, right? It can move up 10 centimeters, right? And so basically what's going to happen is we're looking at what we've seen with a sine wave, right? The amplitude of the wave would be how high this thing swings above and below sea level, right? This is our equilibrium, right? That's equilibrium. That's what I've been calling sea level. So equilibrium is what I've been calling sea level, right? I've been saying that that's that middle line, right? So equilibrium, right? And then the top wave would be this most condensed spring, and the bottom wave would be this most extended spring, right? So what we're told here in this little paragraph is that the displacement from equilibrium is up 10 centimeters and down 10 centimeters, and also that it takes the spring 4 seconds to go through a full cycle, right? So to go from its maximum displacement to its minimum displacement, right, or sorry, from maximum placement above zero to its maximum displacement above zero again. So from here to back to here takes 4 seconds. So basically what we've been told is that the amplitude of this thing is 10 and that the period of this thing is 4 seconds, right? It took 4 seconds for this thing. So we're going to go ahead and talk about some formulae for how you can use this. I'm not going to ask you to memorize them, and we'll talk about that in a sec. So you definitely don't have to memorize what I'm about to do for this class. I 100% do not have it memorized. Your physics teacher probably does. I found in high school that I could logic my way to this formula using math, mostly the stuff that we saw in 4.5 when we talked about the amplitude and the period of sine and cosine functions. If you were looking to do the same thing, you probably could too. So I spent most of that 1996-97 physics class mathing my way through physics, and I probably could have done better at physics if I had memorized formulae, but I found that most of them could be pretty intuitive if you have enough mathematical knowledge. And that's why I want to introduce this here, just so that you have a concept of this real-world application that you'll probably see in a physics class. So for my class, you can use your notes to work through the problems, right? And it's fine to have the formula handy. In fact, you'll see that I actually screenshotted this particular formula and put it on the next 2 slides so we could just use it. So a point moves on a coordinate line in a pattern called harmonic motion or simple harmonic motion if its distance d from the origin at time t is given by either d equals a sine, so this little w, this guy right here, this is omega, right? He's the last of the Greek letters, right? Omega. So a sine omega t, or d equals a cosine omega t. And interestingly enough, the only difference between these two is where the thing starts, right? Because remember that sine, let's just say sine of theta starts in the middle and moves up, right? So like at time t equals 0, it would start at equilibrium and then move up, whereas cosine of theta at t equals 0 starts up and then moves down, right? So it starts up and it doesn't start at equilibrium, right? So just to show you, like, it starts at the top. That's the only difference between those two. All right, and then the last line that we see here, right, the motion has the amplitude of the absolute value of a. That's not a surprise. We actually saw that here, right, absolute value of a. And then the period is 2 pi over omega, or the frequency can be written as omega over 2 pi, and we'll get to that in a sec. So let's go ahead and walk through this. So we're going to go ahead and write an equation for simple harmonic motion of the ball described in the figure, where the period is 4 seconds, right, because t is 4 seconds. What is the frequency? So we're going to assume, I'm going to go ahead and assume that this is start because this is the first picture they gave us. So if this thing starts in the middle, right, so it depends, right? If this is what we're looking at, right? It's unclear where they want us to start. So let me actually rephrase that. So whether you use this one or this one just depends on whether you have this thing start up or at equilibrium or whatever. So you know what? I take that back. Let's go ahead and assume that we start the spring up here to get it started, right? We push it up and then we drop it to let it drop down. So I'm just going to assume that this is start. So if I say that at the start the spring is compressed, right? So spring is compressed all the way up, right? So compressed to the top. So that's saying that at t equals 0, this thing is up. That would mean I'd use this one, right? So I know that the period of this thing is supposed to be 2 pi over omega, and I was told the period is 4 seconds. So I can solve for omega, right? 4 equals 2 pi over omega. So 4 omega equals 2 pi. I think my omega is a 2 pi over 4 or a pi over 2. So now I know omega. I already know that the amplitude of this thing is 10, right? We already talked about that. So if I'm describing that this thing starts at the top, right? If I'm saying it starts at the top and extends past equilibrium and then goes down to the bottom and then bounces back up, then I'm describing a cosine graph. So if I say this, right? If I say this, then I would use d equals 10 cosine of my omega, which is the pi over 2, times t. And that's great. Now, the other option is that you could have said, hey, I want the spring to start at equilibrium. If you'd done that, then you would in all likelihood go ahead and use the sine function. It's the same concept. It doesn't really matter which one you do. Now, sometimes they'll tell you in the problem. So here, they didn't tell me. So since I wasn't told, I just explained which one I chose, right? I wasn't told if this thing started up, down, middle, wherever. Sometimes you're going to be expressly told, and then it's a lot easier. Here, I picked the one I picked because I think logically, if I were going to start this spring in motion, I would probably start it in motion by either pulling it all the way down or pushing it all the way up and letting go. Again, just up to you. So it wouldn't matter. There's multiple correct answers here now. And the next one, there won't be. So now I'm going to use the same formula, right? But this time, they tell me that it starts at its high point at t is 0, right? They tell me that information. So a buoy oscillates in simple harmonic motion as waves go past. It is noted that the buoy moves a total of 3.5 feet from its low point to its high point. So see how the total is 3.5 feet? That means that it's moving 1.75 feet up and then 1.75 feet down, right? So we're going to call equilibrium 0, right? And we see that means that the amplitude, right, the absolute value of A is that 1.75, right? We are told that it starts up at the top. So as soon as I hear that it starts up, I say, oh, hey, cool, that's got to be a cosine, right? And then I'm told that it returns to the high point every 10 seconds. So that must mean that the period is 10, right? And we know that's 2 pi over omega. So when I solve for omega, I'm going to multiply that omega over. So 10 omega equals 2 pi. So omega should be 2 pi over 10 or pi over 5. So seems to me that I want this formula. So my distance is going to be 1.75 cosine of pi over 5t. And that's it. Again, I'm not going to make you memorize this formula. I don't need you to do that. I just want to throw that out there that this is something you might see in a physics class so that it's not completely foreign to you if you do. And that is the end of chapter 4.